Okay. All right. So yesterday we were discussing about the transistor model, right? So let's continue with the portion. Okay. So today let me tell you something about performance parameters. Okay, performance parameters of RE model. Okay. Now, performance parameters in module 2, okay, is related to the four important parameters of any amplifier circuit, and those four important parameters are input impedance Zi, output impedance Z0, voltage gain EAV, and current gain EAI. So this is current gain, okay, and this is voltage gain. V stands for voltage, I stands for current. Okay, and Z0 is the output impedance. Few books says output resistance, doesn't matter. Okay, and Zi stands for input impedance. Impedance. Okay. So this is what we will be calculating in our future classes. Okay. So other day we proposed two RE model, right? The first RE model was for common emitter configuration. So RE model for common emitter config, right? So let's try to extract few details related to common emitter configuration. Right. Fine. So first, let me draw the common emitter configuration. So this is beta RE. Okay. This is base current ID. This is your base terminal, and this is your emitter terminal. And on the output side, you will have your controlled source. Okay. So that's IC is equal to beta times IB, your control source. Okay. And your output terminals, collector and emitter. Okay. Let us mark few of the performance parameters. Across the input port, you have Zi, and across the output port, you have Z0. Okay. And then we'll also mark the standard, two-port network current directions. Inward current direction is for II, and once again, inward current direction is for, output current. Okay, so this orange color, okay, basically represents two-port network parameters. You see, transistor has one input circuit and one output circuit, right? So that's the reason, it can be modeled into a two-port network. Similarly, the transformer can also be modeled into a two-port network, because transformer has an input circuit and also has some output circuit. Okay, so transistor, transformer, transmission lines, everything can be modeled into a two-port network. Okay, more of it you are going to study in network analysis. All right, fine. So that being said, I think we can go ahead with estimating the performance parameters. All right, so first let us take up Zi. Okay, so what I will do, let me also mark the input voltage, and let me also mark the output voltage. Okay, so input voltage Zi, by definition, it can be defined as Vi by II. Okay, and Vi can be written as, what is Vi? Vi is voltage across the resistance beta RE. So that is nothing but current into resistance. So that's actually II into beta RE divided by II, which is equal to, what is II? II is IB into beta RE divided by, again, II is IB. Okay, here itself you can cancel out, but I wanted you to understand that input current is nothing but the base current. So you would get beta RE as your input impedance. Okay, and I have already told you expression for RE is given by 26 millivolt divided by DC current IE. Okay, so the normal range for RE is only few tens of ohms. Okay, only few tens of ohms. Since your RE is getting multiplied with beta, okay, and you know that beta is in the range of hundreds, okay, 100, 200, 300, etc. So that's the reason your beta RE is significantly larger. Significantly large. So normal range for your input impedance is in few kilo ohms. All right. So that's your input impedance. Okay. Next up, we have the output impedance Z0. So this output impedance Z0 can be calculated, okay, by looking into the output port. So Z0 by definition is output voltage by output current, right? Now, if you look at the output circuit, okay, you are trying to measure the output impedance across what? You're trying to measure the output impedance of an ideal current source. Okay, so it is basically impedance of ideal current source. Okay, can anyone tell me what is the impedance of ideal current source? An ideal current source is a current source which gives constant current to the load irrespective of the voltage variations taking place at its terminal. So that means to say, whatever may be the changes in the load condition, an ideal current source keeps on giving constant current. So that means to say the impedance of ideal current source is actually infinity ohms for ideal current source. Okay. However, transistor being a practical device, so ideality cannot be considered while solving the problems. Okay. Hence, we define the practical range. So practical range for Z0 is in the order of few tens of kilo ohms. Okay, typically say 20 kilo ohm to say up to 40 kilo ohms. So that's the usual range for your Z0. All right. So that's Z0, and then you have the voltage gain AV. Okay, voltage gain AV is defined as the ratio of output voltage to input voltage, right? What is output voltage? Okay, so in order to write an expression for AV, what we will do is let us connect a load resistor. Okay, let us connect a load resistor. So what I will do, I'll just delete this part to add more clarity. Let me remove off the unwanted, blockages. Okay, fine. So what I have done, I have connected an external load resistor. Across the load, I'm going to measure the output voltage. Okay. Now remember one thing, we will be fixing the polarity of the output voltage as upper side positive and lower side negative, simply because emitter is held at lower potential. All right. Fine. Now, this is how the actual load current flows. When the current flows into the load, the polarity of the output voltage attains, this particular polarity sense, right? Fine. Now, what you have to observe is that the two-port current direction is inward. On the other hand, actual current which is flowing through the load is flowing in outward direction. So there is, what you say, conflict of current direction. That's okay. We will consider along with the sign. Okay, fine. Let me go back to V naught. So V naught, by definition, you can write it as, let's say, okay. Now, V naught, I want to write it as I naught into RL because my output current, I have defined it as I naught. Okay. Now, with the assigned direction of I naught, okay, so how am I have assigned the direction of current I naught in this manner, right? Lower to upper side. So your actual output voltage due to, I naught appear in flipped manner. That means to say, the voltage across RL for the direction of I naught is opposite to that of the V naught convention, right? So what I can write over here is that V naught is equal to minus I naught into RL. In bracket, let me write I1 is in opposite direction compared to IN. Okay, just because of the opposite, current flow, you will get, the negative sign. Okay, also, I naught is equal to IC. That's because I naught and IC current direction is agreeing with each other, right? IC is flowing downwards, and so as I naught. So IC can be taken as I naught. Okay, and therefore you can write your output voltage as minus IC into RL. Okay, let's keep it aside. And then let's go back to the input voltage expression. Input voltage VI is equal to, you can take it as II into beta E or IB into beta RA. So what do we have? We have the expression for two voltages. Let's divide them. So V naught is equal to output voltage, that is minus IC into RL, divided by VI. VI is IB into beta times RA. So take out this ratio. IC by IB is what? Beta. So it is beta into RL divided by beta into RA. So beta gets cancelled, and you will get the output voltage, the voltage gain as negative RL by RE. Okay. Now, what's the meaning of this negative sign? The meaning of this negative sign is that output is out of phase with the input. Okay, that means to say, if your input is a positive going signal, okay, let's say this is your input. So in the 0 to pi interval, your input is positive bound, and let's say from pi to 2 pi interval, your input is negative bound. On the other hand, in case of common emitter amplifier, what happens is that the wave appears in a flipped manner. So you would get a complementary wave in the output side. All right. So instead of having a positive going signal between the interval 0 to pi, you will have a negative going signal. Okay. Now you can clearly observe that they are 180-degree phase apart. Okay. So they are 180-degree phase apart. So that is called as out of phase phenomenon. Okay. So this negative sign indicates 180-degree phase shift. All right, fine. So that's about your voltage gain. And finally, we have our current gain AI. Current gain AI is defined as I naught by II. Okay. So I naught is IC and II is IB. So IC by IB ratio gives beta. So beta is your current gain. So this is how we calculate what you say, the performance parameters of C configuration. Okay. Now this they may ask, okay, in exam. Normally what they will do, they will not ask you this type of derivation, because this type of derivation is very simple. Normally they'll ask you to find out the performance parameters along with the biasing circuit parameters. Okay, let's look at it a little later. Okay, so that's about your first RE model performance parameter. Now let's take up the second RE model performance parameter, that is common base RE model. All right, so let's look at common base RE model. Okay, and let me draw the circuit first. I think you can do it along with me. So in case of common base RE model, your input resistance is RE, and this is how you had drawn the current source, right? This is your emitter terminal and base, and collector. So this is IC is equal to alpha times IE, and this is how you had defined the direction of IE. Okay, and this is your input voltage plus minus. Okay, and somewhere here across the output node you will be observing the output voltage. Okay, all right, and let us also mark the standard two-port network current directions. Okay, inward current II, and once again the inward current from the output port as well. Let's take it as I0. Okay, and yeah, fine. Let's start finding out the performance parameters. Let's start with input impedance, Zi. So Zi is Vi by Ii. Okay, so Vi is input current into resistance, so IE into RE divided by input current is IE, hence you would get input impedance as RE ohms. Okay, so I've already told you RE can be calculated from this particular semiconductor diode equation. Okay, 26 millivolt divided by IE. So RE is very low. Okay, so usual range will be somewhere about 10 ohms to say some 20 ohms. That's all, very, very low. So this is a feature of common base transistor configuration. It gives very low input impedance. So if your load is also very low, I mean, if your load is having very low impedance, probably not the load, source I'm talking about, because you connect source here, right? If your source is having, say, ohms of impedance, okay, then you can go for common base model, because even your common base model gives an input impedance in the range of ohms. So when you connect the two impedances, which are comparatively closer to each other, then you can achieve maximum power transfer theorem. So maximum power can be delivered from source to the load. Okay. On the other hand, if you look at common emitter configuration, let's say suppose your source is having few ohms of impedance, okay, and you have seen that your common emitter configuration is having an input impedance in the range of kilos of ohms. Okay, so in kilos of ohms. So you are trying to connect a source having a few ohms of impedance to a load which is having kilo ohms of impedance. So there is a clear mismatch in impedance, and due to this mismatch, the power delivery won't be that good, and hence the signal loss may happen. Okay, so that's the importance of impedance matching. So this is how you can achieve impedance matching. Okay, nevertheless, let's go ahead. let's continue with the output impedance Z0. So output impedance Z0 is given by V0 by I0. Okay. Now your Z0, once again, it represents output impedance of a current source, because on the output side, what do you have? You have a current source. So Z0 is nothing but output impedance of current source. Okay. And in the previous class, I have already told you the output side, you have a collector layer and you will have a base layer, and the conductivity is low for base layer and conductivity is high for collector layer, simply because collector will have more dopants and base will have less dopants. Okay, that's the reason on the output side the output impedance is significantly high compared to common emitter configuration. Okay, so in common emitter configuration, your output impedance range is usually up to few tens of kilo ohms. On the other hand, since there is low conductivity base layer present across the output port, what happens is that your Z0 range shoots up. Okay, Z0 range is very high. Okay, as high as few mega ohms. Okay, it will be there. It will be in the range of few mega ohms. This is a practical range I'm talking about. Okay, this is the practical range. Practical range. Okay. Always remember, this is one of the important questions in Viva. Why the output impedance of common base configuration is greater compared to common emitter configuration. So answer would be, in case of common base configuration, across the output, the base layer is coming into picture, and base is having lower conductivity level. So lower conductivity means higher insulating property, and due to which the resistance shoots up, and that's the reason the resistance is normally found in the range of few megas of ohms. Fine. So that being said, we are done with the output impedance calculation. Okay. The third one is the voltage gain, AV. So AV once again can be found using the formula V0 by Vi. Okay. And to find V0, what we will do is we will connect a load resistor. Okay, let us not consider what you say no load gain. We will consider gain under loaded condition. All right, so this is how we have fixed the polarity. Okay, so that means to say, to get this polarity, your output current the load current should flow in this direction. But as you can clearly observe that in the two-port network topology, we have assigned the output current in the left-hand side direction, right? But your actual current flows in the right-hand side direction. That's the reason, your output voltage will appear in flipped manner. So V0 can be given as minus I0, yeah, I0 into RL. Okay, minus I0 into RL. Okay, next, what is I0? Can anyone tell me? What is I0? Can anyone tell me what is I0? With the sign, you are supposed to tell me. Okay, it's been almost 40 minutes. I'm only talking. So I'll just pause for a second and let me ask you, what is I0 for common base configuration? Along with the sign you are supposed to tell me. Can anyone tell me?
Minus of IC.
Exactly. Superman. Good. Okay, so I0 is minus IC. Okay. Therefore, your V0 becomes minus IC into RL, or this is IC into RL. All right. So that's your V0. See, this is very, very important. All right. So this is how we get trapped in module 2. Okay, that's the reason the normal tendency is that students they keep complaining that module 2 is difficult. Okay, if you by heart, it is difficult. If you understand, it won't be, that difficult. All right, fine. Fine. So V naught is IC into RL. Remember one thing, okay, unlike CE configuration, this has a positive sign. That means to say no signal inversion. No signal inversion. Right. Now let's look at VI. So VI is II into RE. Okay. So let's divide them. So AV is equal to V naught. So V naught is IC into RL. All right. And divided by VI. What is VI? II into RE. That is equal to IC into RL divided by II. So II is the emitter current into the resistance. So IC by IE ratio is your alpha. So voltage gain is alpha into RL divided by small r. Okay. So once again, I want to reiterate that your voltage gain is having positive sign. That means to say, if you go for a common based amplifier network, you will not find any signal inversion between the input port and the output port. Okay, so let's say this is your input signal, and your output signal will also be the same in the sense phase. Okay, of course the amplitude will be increased in case of amplifier operation. Okay, the phase going to be the same. For the positive going input, you will have a positive going output. Therefore, phase shift between VI and V naught is 0 degree. Okay, fine. So that's your voltage gain. And finally, we have the current gain. Okay, current gain AI. So current gain AI is equal to I naught by II. Okay, so I naught is equal to minus IC. Remember, as one of your friend told, IC and I naught are opposite in direction, right? So that's the reason I'm substituting I naught as minus IC. Okay, divided by II. II is IE. So basically, you would get minus alpha. Okay, but normally we don't consider minus alpha or plus alpha. Okay, we always consider current gain with the modulus. Okay, always we take current gain as positive. Doesn't matter as per the equation is concerned. For common base configuration, you would get negative alpha. Okay, so that's how you calculate the current gains. Okay, is it clear? Do you have any doubts? Okay, so this being the foundation, we can start analyzing practical the biasing circuit. Do you have any doubts? I'll take a pause here. No? No doubts, right? So if I don't get your reply, then what is the point? I mean,
It's clear, sir.
Yeah, I can simply record the video and send it across, right? Why should I disturb you also? Okay, fine. All right. So now let us look at few general steps which are used to solve AC circuit problems. Okay, AC circuit problems. Fine. So what I will do, yesterday I have broadly told you about how to handle AC circuit problems. Okay, nevertheless, you can take down the question in the solution itself. Let me tell you how exactly you solve the problem. Okay, so write down for the fixed bias, based amplifier circuit, determine ZI, Z0, AV, AI. For the fixed bias circuit, for the fixed bias based amplifier circuit, determine the following. Okay. All right. So let me draw the circuit diagram. RB, RC plus VCC. Okay. This is your input capacitor CI. This is your output capacitor C0. And this is where you measure your output with respect to ground. And this is where you feed your input with respect to ground. All right. Fine. So, fine. So this is the given circuit. Okay. Now, step 1. Isolate DC conditions. Okay, so in step 1, we are supposed to isolate DC condition. That means to say we are applying superposition theorem. Okay, don't worry, you'll come to know about it. Okay, superposition theorem. It's basically network, simplification theorem using which you can handle a circuit which is under the influence of multiple sources. Okay, so what we do is we apply superposition theorem to isolate DC operation in the sense, let us set VCC is equal to 0. Okay, let us set VCC is equal to 0. This is also called as, sometimes we say ground VCC. Okay, so I'm, forcing VCC to 0. Okay, just to, have AC conditions in my system. Okay, that's my step 1. Okay, in step 2, okay, what I will do is let me replace the capacitors. Okay, replace capacitors with short circuit equivalence. Okay, short circuit equivalence. Question is why? I think yesterday I have told you. So capacitors allows the flow of AC current, right? So capacitor allows the flow of AC current. So for AC, okay, for AC, capacitor can be replaced with a short circuit equivalent. Okay, a capacitor can be replaced with a short circuit equivalent. So what will happen is you have your input capacitor, right, CI, and you also have an output capacitor across the output node. So these two capacitors we are going to replace with a short circuit. Okay, with a short circuit. Okay, that you will be doing it in step 3 and in step 2, and in step 3, reassemble the circuit in an appropriate way. And insert RE model. Insert RE model in place of transistor. Okay, so insert RE model in place of transistor. Are you finding it difficult to understand these steps? No worries. Let us put to use these steps and then you will be able to understand. Okay, so I'm just going to write down the crux of the above 3 steps. Okay, so in step 1, what is that we are supposed to do? We are supposed to ground VCC. So let's do that. You have, RB. You also have an emitter circuit. Okay, you have, what do you say, RC. Okay. So what are we saying? We are saying ground VCC. Ground VCC as in connect the other end of RC to ground, because in a previous step, this RC was connected to plus VCC, and also this particular end of RB was connected to plus VCC. Now we are grounding their terminals. Okay, so grounded. All right, and that's your step one. That's your step one. Okay, that's all. Step one. Is it understood? Can I get a quick yes or no in your chat box? Okay, good, fine. Next step, let us apply. So step one is done. So let me cut it. Step two, what is that we are supposed to do? We are supposed to replace the capacitor with short circuit equivalent. So earlier you have had a capacitor at the input terminal, right, in this manner. So what I'm going to do is I'm going to replace that capacitor with short circuit equivalent, erase it, and just connect it with a straight wire. Okay, straight wire. This is where you are going to feed your input. Similarly, there was a capacitor on the output side. Okay, let me show you here. Okay, this particular capacitor C0 that I'm going to replace with a short circuit equivalent. So just connect it with a straight line. So this is where I'm going to measure my output. Okay, done. So we have finished step one as well as step two. Okay, so while stating we found it little lengthy, but when we using it, when we are basically applying it, you can understand that it is very simple. All right, so step one is done. Step two is also done. Okay, now let us apply step three. So in step three, what did I say? Let us rearrange the circuit in an appropriate manner. That means to say, what we will do is just draw the transistor here. Okay. What I'll do, I'll just go down and I'll do it somewhere over here. Okay. So draw the transistor symbol as it is. Collector, emitter, and base. Okay. Now, to the base terminal, RB is connected, and other end of RB is grounded. So what we can do is, to this base terminal, we can connect RB, and other end of RB is grounded. Okay, and we also know that emitter is also connected to ground. So we can drag this emitter terminal, and we can connect it to ground. Okay. And the same base terminal is then connected to the input, right? So just draw a wire and connect an input here. Okay. So input is connected across the base node and the ground node. Okay. So this is my input. Okay. All right. Now let's pay our attention to the output circuit. So what do we have on the output circuit? We have the collector terminal here. Okay, to the collector terminal, RC is connected, and other end of RC is grounded. So as simple as that. So RC is connected, and other end of RC is grounded. Let's ground, and across collector and ground, output is observed. Okay. Now what you have to do is you have rearranged the circuit in a appropriate way. Now you have to finally replace the transistor symbol with the equivalent RE mod. Okay. So what I will do, this is my two-port device, correct? This is my two-port device. Okay, now what you have to observe is that this particular transistor is connected in common emitter mode, right? It is connected in CE mode. Hence, replace this common emitter mode device with RE mode. of common emitter mode. That's all you are supposed to do it. Okay, let me show you how to do it. I go down so that it had better clarity. What I will do, I will just write down the base terminal. Okay, and first let me connect the external circuit elements such as RB, and also let me connect the input voltage Vi. Okay, so other end is grounded, so be it. And this is also held at ground potential. Okay, and on the output side, I have my collector terminal somewhere over here. Okay, and to the collector terminal we have connected RC. Okay, RC, and across RC I have the reports of all my labs. Open course meet. Okay, this is RC. Fine. Now, in place of transistor symbol, let us substitute the RE model. Okay, let me show it here. So what I will do from base, okay, I'll connect it to beta RE, and from collector I will connect it to beta IB. That's all. And that is your RE model. Okay. If you want further simplification, probably what you can do is you can connect all these grounds together. Doesn't matter. Okay. So this is your RE model. This is how we construct the RE model. Okay. Once you have the RE model, then you can determine the performance parameters such as Zi, the input impedance as seen from the input terminals, Z0, output impedance as seen from the output terminal. Okay, and then AV and AI. Okay, let us also mark the transistor currents. This is base current IB. Okay, and this is collector current IC. Okay, which is given as beta times IB. And also let us mark the standard two-port network terminology signals, the input current II and the output current I0. Okay, output current I0. Okay, so this is how we construct the RE model of any given circuit. Fine. It is 9:29, so I will stop today's class. So what I will do is from next week onwards, first let me solve this, and then let me solve collector base bias, emitter bias, and voltage divider bias based amplifier circuits. Okay. All right. So did you understand? Once you get this model right, then things are very easy. Okay. Fine then. So can I conclude today's class? Okay. All right then. So let's meet on say Tuesday, right? Yeah.